Welcome, everybody, and thank you very much for joining us for today's Department of Energy Lab Discovery Series webinar. My name is Mike Paulus. I lead the Oak Ridge National Laboratory Partnerships Office, and we're excited to share with you one of the technologies that we think has the potential to make a real difference. I'm joined today by two ORNL researchers, Omer Onar and Mustaq Mohammed, and they developed ORNL's Polyphase Wireless Power Transfer technology, and that's the topic of our webinar today. I'm also joined today by Eugene Cochran. Eugene is ORNL's Technology Commercialization Group Leader, and after Omer and Mustaq present, he's going to talk a little bit about the process for licensing a technology from Oak Ridge National Laboratory or from any national laboratory. And then following Eugene's remarks, I'll speak briefly about the other mechanisms for partnering with the national labs. And you'll notice I have a very fancy QR code behind me. I'm proud that I finally learned how to do that. If you want to snap that, it'll take you to a guide for partnering with the national laboratories, and it tells you about the various mechanisms that we have. Before we kick off the technical presentation, I'd like to remind you that your microphone will be muted throughout the presentation, but we'd love to have your questions. So if you could drop your questions into the Q&A box at the bottom of your screen, we'll go through them at the end of the presentation. And now, without further ado, it's my pleasure to introduce Omer and Mustaq to talk about wireless charging. Gentlemen?
Thank you very much, Mike. So good afternoon, everyone, and thanks for calling in. As Mike mentioned, today's speakers are myself, Omer Onar, and my colleague Mustaq Mohammed. But you see the detailed bios here, but we are really the applied power electronics and electromagnetics researchers at the laboratory, working on innovative technologies for transportation and electrification. And wireless charging since 2008 has been a big program at the laboratory, and we are a part of a much bigger group. So there's quite a few people working on the technology between multiple projects and activities for wireless power transfer systems. And of course, electric vehicle charging is one of the attractive application areas for wireless power transfer. So let's jump into the technical content. So a lot of times you may think about plugging in is an option that is already working. On the other hand, you have to deal with this heavy duty at the same time and dirty and difficult to handle wires and plugs and cables. It's a tripping hazard in highly populated areas. There's wear and tear on the cables that is exposed to the weather conditions. And in big cities, on the sidewalks and bike lanes, there are people trying to plug in their vehicles. It's just not the way we need to actually recharge the electric vehicles. We're in 2024. And if you asked me 10 years ago this question to promote wireless charging, one thing that we were saying is that you don't forget to plug in charging and run out of charge the following day. That's a really good convenience in additional functionality that wireless charging brings. But today actually it enables a lot of different things. One really hot topic is, of course, the connected and automated vehicles. A lot of automotive OEMs, even graphic processors, computational companies invest a lot of technologies on the connected and automated vehicle systems. These vehicles can self-drive, self-park. They can even make route planning, fuel-saving decisions, time-saving decisions. However, you need to have someone to plug them in and unplug them. So you actually don't have the automated charging process. With wireless charging, we can fully automate the charging process for the electric vehicles. The other benefits is, of course, aesthetical reasons, right? Appearance in front of the historical buildings or historic districts. You just don't want to see those wire mess. And weather conditions is the other thing. Ice, rain, snow. A lot of times in harsh weather conditions, the plug may freeze inside the inlet. With wireless charging, actually, this doesn't happen. Yeah, as a byproduct, you can also melt some snow around your transmitter and receiver coils. And in crowded facilities, for instance, we have a project with UPS. Loading docks and sorting facilities are merged together. There's just not room for pedestals for each vehicle and the wire and cable mass. So wireless charging actually fully it blends in together. You can actually have the primary side hardware underneath the box with the transmitter actually underneath the vehicles. So when the vehicles park for unloading, you can actually start charging. So I mentioned that wireless charging or wireless power transfer research at the Oak Ridge National Lab started in 2008. And since then, we had a lot of accomplishments. Actually, the 20 kilowatt wireless power transfer back in 2016 was a big accomplishment because a lot of systems were at 3.3 kilowatt power levels. So we had about 6 times higher power back in 2016. Now, actually, we have 100 kilowatts, 270 kilowatts stationary high power wireless power transfer projects. We also have low to mid power for mainstream vehicles, 20 kilowatt to 50 kilowatt applications. And we have a project on dynamic wireless power transfer to charge the electric vehicles while they're in motion to reduce range anxiety. And we also have the bidirectional, fully grid integrated, medium duty vehicle integrated facility deployed projects on wireless power transfer systems. We also work on innovative power converters, unmanned underwater and unmanned aerial vehicle applications, long distance wireless power transfer applications. About 10 meters power transfer distance is now possible. And we are also thinking about technologies that can power portable electronic devices from a single transmitter. Just like today, we are receiving the Wi-Fi signals for internet connectivity on our devices. We can have power transfer actually for those portable electronics, eliminating all the chargers and cables and plugs and all that. And we are also always targeting higher frequency for a lot of the benefits that it provides. Not silicon devices anymore, but all silicon carbide and gallium nitride. So with that, we can get into the more technical content on polyphase wireless charging systems. We see that this is really an enabling technology for high power electric vehicle wireless charging applications. So we actually have a project that's we are completing. We have done the demonstrations, one for DOE, another for the partners, and the second demonstration we did it for the partners and waiting for DOE. So the target on that project was to significantly increase the power levels and efficiency of the wireless power transfer systems with the most compact and lightweight couplers possible. And we targeted getting close to 3C charge rates. That means 50% increase in state of charge in 10 minutes. That actually brings us very close to today's gas station refueling experience that we have. And you'll see that we have more than 95% efficiency, although the project requirement was 90% efficiency. And we have 4 inches of misalignment tolerance in any direction. So typical parking behavior is kindly accounted for within the system performance. And it meets the ICNIRP guidelines on electromagnetic field emissions, even without using any shielding. So a lot of systems for wireless power transfer for electric vehicles is limited to 6.6 and 11 kilowatt power levels. Even the standards today don't include power levels greater than 11 kilowatts. The reason is that they think that especially more than 22 kilowatts, the coils will be prohibitively large and heavy. You cannot really have a light-duty passenger vehicle wirelessly receiving, hundreds of kilowatts of power. Now, actually, today we are changing it, and you're seeing our technology. And a lot of systems have 50 to 100 kilowatts per meter square power densities. You'll see that we are also not improving this by 10-15%, but 8 to 10 times. And these 6 kilowatt, 11 kilowatt systems are struggling with the ICNIRP compliance, that is the organization that regulates the electromagnetic field emissions. So you'll see that our systems are ICNIRP compliant. So what was the motivation? Why did we look into the polyphase systems? Single phase systems actually pulse the power across the air gap. That results in very low space-time average utilization of the fields. If you look at a three-phase system, at a given time, each phase delivers an amount of power. So you have constant power transfer to the secondary with significantly reduced ripples, and at the same time, substantially improved space-time utilization of the fields. So we have the phases 120 degree apart from each other, and we electrically excite them with that same electrical phase shift. So with that, we have much higher power density and low current ripples and voltage ripples, both at the input and on the vehicle side. And we also have each phase supporting each other instead of having some magnetic field cancellations. So they all work together to actually boost up the power. And some animation on the rotating electromagnetic field concept. Of course, in reality, this happens so much faster. I think it is 5.1 mega RPM speed. You see the slowed down version here so that our eyes can sense it. And some comparisons with the existing systems. These are not our numbers. These are the numbers that they advertise, either these developers or universities or manufacturers, either from their newsletters, flyers, technical data sheets, or publications. So these are the power levels and these are the dimensions that they have. So based on that, a lot of systems in the world have about 50 to 150 kilowatts per meter square power density. What we have on our 100 kilowatt system has about 0.9 megawatts per meter square, and our more recent development for Porsche Taycan has 1.5 megawatt per meter square. Of course, this table provides a good comparison. We are all people of data, but sometimes we tend to visualize things and it's more descriptive. So compared to all these other systems in terms of kilowatts per meter square power density, this is the coil that we have on Porsche Taycan today, and this is the coil we have on Hyundai Kona today. That actually significantly improves the power density of the systems. So the coils can be a lot more compact. And in terms of the weight, again, we have a similar figure compared to the existing 250 and 200 kilowatt systems that are 200 to 300 kilograms. Our coils are much more lightweight. So that's how actually we enabled the high power wireless charging for even light duty passenger vehicles. And here is another comparison, how heavy the receiver coils could be if they were normalized for 300 kilowatt power rating. So a lot of these systems are in reality 500 kilograms to 300 kilogram systems, and our systems have much less weight compared to the others. So a little bit more details on the coil designs and magnetics.
So this diagram shows the presentation of two different high-power wireless charging system. One is 100 kilowatt and the other one is the 300 kilowatt. So the left diagram shows the 100 kilowatt / 300 kilowatt interoperable ground coupler. That is the size is the 750 millimeter. The second one is the 500 millimeter diameter 300 kilowatt system. And the third one is the 100 kilowatt receiver. The dimension is only 375 millimeter. And the three other picture shows that the experimental prototype. Now at the bottom of this slide, we see that the power density, and for the receiver, we see that the power density of the 300 kilowatt system goes as high as 1.53 megawatt per meter square. One of the main motivation of making the transmitter is to make it as universal as possible so that it can provide 4 inches misalignment tolerance in all direction. And it has to be interoperable with for different power classes. For example, for this system, going to 100 kilowatt to 300 kilowatt, the transmitter side kept exactly the same, only the receiver side is changed. So if we need to go for example, 200 kilowatt system, or instead of 400 volt, if we need to go to 800 volt system, then the only part that we need to change is the receiver and its tuning component. So that makes the system, especially the transmitter, highly interoperable with all the high power wireless charging systems. We can go to the next slide. Thank you, Omer. So now, as we have solved the electromagnetic solution for the coupler, how about the power electronics and overall system architecture? One key requirement is the interoperability. interoperability with the single phase and the three-phase system, and also the misalignment tolerance. So this one shows the open-ended circuit diagram of overall three-phase system. So we have 3 primary winding, 3 secondary winding, and each of the winding is compensated by LCC compensation, and they are connected to the primary side inverter and the secondary side rectifier through open-ended connection. So what we have in the primary side is 2 three-phase inverter. They work such that there are effectively 3 full bridge inverter. At the same time, on the secondary side, we have 3 full bridge rectifier. So that makes the receiver interoperable with any single phase system. At the same time, if we have a single phase receiver, that is also interoperable with this 3-phase transmitter. I think we can go to the next slide. So this is the prototype of the primary side inverter. So on the right diagram, it shows that we have the phase leg A, that full bridge inverter at the bottom, then in the middle phase B and phase C. So we have used the custom designed PCB-based bus bar, and the overall power density became extremely high, and overall power density became 54.5 kilowatt per liter. And in the next slide, we'll show the rectifier design for the secondary side. So for the secondary side rectifier, we compared 2 different devices, and it came out that the Schottky diode, silicon carbide Schottky diode, was much higher in power density and the lower in the loss. So on the right, it shows the design and the prototype of the rectifier. Now, due to the change in the 100 kilowatt to 300 kilowatt, 400 volt versus 800 volt, it came out that the same rectifier was used both for 100 kilowatt, also for the 300 kilowatt system. On the next slide, we'll show the overall lab setup in the lab. So on the left side, we have the inverter, the 3-phase inverter, 2 3-phase inverter, and the rectifier, the relative size. And the right figure shows that the overall setup where we do most of the high power stationary and the dynamic wireless charging system. And at the center, we have the Porsche icon, which is probably one of the main attention, and it can take up to 270 kilowatt power. So I think for both the test, we use the vehicles, and what the vehicles provide is much more insight than only the lab setup with only the coil. So now in this one shows the stationary or the vehicle assembly power electronics. So everything goes under the box. So we have the inverter, we have the resonant unique capacitor and the inverter. And on the next slide, it will show the vehicle assembly. So everything for the 100 kilowatt system, it's integrated into a front of the Hyundai Kona. So it includes the rectifier, the tuning component that's include the resonant tank capacitor and the inductor. And apparently it came out that from this 100 kilowatt system, the 300 kilowatt system even became smaller in the overall vehicle assembly. And the coupler is placed at the front of the vehicle under the chassis. So this is so at the beginning, we used a 300 kilowatt, 300 to 400 volt range. But these Hyundai Kona can take only up to 75 kilowatt, and our target is testing the system at 100 kilowatt. And that's why we had to put a resistive load inside the vehicle that can take the 100 kilowatt. So that resistor became 3.2 ohm. And so at the beginning, we tested the system outside the vehicle that was 96.3% efficiency. And one of the main attraction was, okay, what will happen if we integrate into the vehicle? What will happen to the emission, to the efficiency, to the loss, and all the thermal effect on the vehicle? So we put the probe on the next to the vehicle at the closest proximity, and we tested the electromagnetic field emission. So this one shows the electromagnetic field emission next to the vehicle. And at full 100 kilowatt power at 0.9 meter away, which is closest to the vehicle, the magnetic field was 16.81 microtesla RMS. So the limit is 27 microtesla by the ICNIRP. So at even 100 kilowatt system, we are close to much below the safety limit. And the next slide will show the test results that one of our partner took. The power is going from all the way up to 100 kilowatt, and at the lower of the chart is showing the loss and the efficiency. And as we see, the power is now still very low. So as the power is increasing, it's around 1 kilowatt now. So now it's 5 kilowatts. So as we see, it's as soon as it is 5 kilowatt, the efficiency is already 93.5%. So I think the next step will be the 10 kilowatt power. So we see that it's 94.6%. So on the left side, we have the input voltage, current, and the power. On the right side, we have the output voltage, current, and power. So now it's 20 kilowatt input power. At the lower of the screen, we have the power loss and the DC to DC efficiency. So this is 20 kilowatt. So at 25 kilowatt, 30 kilowatt. So as we see, as the power goes above 10 kilowatt, the efficiency is almost stable and always higher than 93 to 94 and 95%. So it has also very good low power efficiency. This is approximately 60 kilowatt. 93 kilowatt, and now we have 199.6 or close to the 100 kilowatt, and the overall efficiency is 96.003%.
Okay, so now that we completed the 100 kilowatt demonstration, we also worked on our next target, which was 270 kilowatts on the Porsche Taycan electric vehicle. So this Porsche came all the way from Germany as a part of Volkswagen's partnership in the project. So this vehicle already had space allocation for an 11 kilowatt wireless charging system underneath the vehicle. They didn't have the wireless charging unit, but they had the space allocation. So what we did was in the same space that they allocated for 11 kilowatt system, we were able to fit our 270 kilowatts receiver coil. I think in one dimension it was a little larger, in one dimension it was a little smaller. So at the end, more or less, although the power is significantly higher, we were able to integrate our coil into the same space that was designed for the 11 kilowatt system. And also the coil got kind of almost leveled up with the vehicle chassis without sticking out significantly. Not a huge reduction on the ground clearance of the system. And the original system actually used 3 wires per phase running in parallel and 2 turns. Since Porsche Taycan had the 800 volt battery, we actually had a slight change in the design. Instead of 3 wires in parallel, we had 2 wires in parallel. So that saved actually 6 wires in total from the vehicle assembly. And it became actually a less dense system in terms of the wires. And since the voltage is higher, instead of 2 turns, we actually had 3 turns in the system. And a little bit more pictures between the vehicle cross members, how the receiver coil was integrated. And on the electronic side, we use the frunk area, which is the frontal trunk in most of the electric vehicles. So they had this space above the fans and valves and pumps and the liquid cooling system of the Taycan. So we were able to package our 270 kilowatt vehicle side electronics within this given space. And this was a 2-layered approach. The bottom we had the tuning capacitors, and at the top layer we have the resonant tuning inductors and the rectifiers. And we also had the electromagnetic field emissions here. I don't know if we put the results, but Mostak showed that at 100 kilowatts, we had about 16.8 microtesla field emissions. At 270 kilowatts, we had about 20 microtesla field emissions, still below the 27 microtesla ICNIRP limits. So that's one advantage of the polyphase, right? In single-phase systems, since the fields are static, at a given point, you see the peak of the magnetic field emissions at any time. In our approach, since we have rotating magnetic fields and each phase carries about 1/3 of the power, we have actually less than 1/3 of the field emissions that you would see in a single phase system. So at 270 kilowatts, we had about 95.4% efficiency, which is really, really good. And we have the input voltage, current, and power, output voltage, current, and power. On the vehicle side, the vehicle battery is about 640 volts, kind of an 800-volt battery when it's closer to the lower end of the state of charge. And we also wanted to validate this number with a second power analyzer that is also in calibration. And on this one, actually, we saw 95.4% efficiency instead of 95.43% efficiency. So that's within the tolerance of the sensors and probes. So we validated with the second instrumentation that we have 95.4% efficiency. And these are the operational waveforms for the 270 kilowatt system, the three-phase inverter output voltages and current, and then the input inverter input DC voltage and current. And then we have the vehicle side rectifier, all three-phase voltages and currents, and then the DC output voltage and current that is going to the load side on the system. And we also wanted to characterize the performance of the system across the full power range. So this graph shows the efficiency between 10 to 270 kilowatt power transfer with 10 kilowatt increments. So we have the high efficiency across the full power range. As you can see, anything more than 20 kilowatts or so, we have about 95% efficiency, and efficiency peaks at around 80 kilowatts. 90 kilowatts. That means about 30 kilowatts per phase power processing. So we have 95.4% efficiency. The 270 kilowatts point is a little less efficient. That's just because we have 400 amps of current at the input side, 400 amps at the output side. So we have more conduction and copper losses and all that. But if you look at a lot of the plug-in high power charging stations, at 20 kilowatts, 40, 50 kilowatt power level, their efficiencies can be as bad as 70%. Since we are using high frequency, wide band gap devices, that semiconductor technology is actually more superior. And also our electromagnetics designs in three-phase assembly performs really, really good for the power levels that we have. So next, actually, we are starting projects at even higher power levels, 750 kilowatt power level. But at the same time, for the mainstream electric vehicles, overnight garage residential charging is still a big application. So there is an interest from the automotive OEMs for systems focusing on 11 kilowatt, 22 kilowatt power range. And our Polyphase system, not beneficial only at high power levels, but at 22 kilowatt system, it can be still a lot more compact than the circular or double D type of coils. So that's the other research area that we are exploring. So I think that's all we have. We're going to get back to Mike Paulus, and he will actually provide the information on the licensing and partnership. And I think we'll get back to the questions and answers after that.
Outstanding.
Thank you, Mike.
Omer and Mustak, thank you very much. I'm always impressed with the performance you guys have managed to get out of these systems. I also want to thank Sean Sullivan and the DOE Office of Technology Transitions for making this platform available to us and for arranging this webinar series. It's really nice to have a chance to connect with folks that are interested in these technologies. Before I talk about other power mechanisms, I'd like to hand the floor over to Eugene Cochran, and he's going to speak briefly about the process for licensing this technology and other similar technologies.
Okay, thank you very much, Mike. So yes, this is one of many opportunities that are available through our partnerships office, and I'm the group leader for the commercialization team, which generally translates into licensing. So we help our investigators secure patent rights around their inventions, and then in turn try to foster the adoption of these technologies in industry through patenting and licensing. So if you do have interest in this technology, we are making it broadly available to industry on a non-exclusive basis. And further information can be found by just emailing me. And my last name is Cochran, COCHRANER at ornl.gov is the email to reach me. And I can help guide you through our licensing process, be it the identification of the IP that you're interested in. We allow you to due diligence and evaluate those opportunities. We then ask that you submit a licensing application. We review that application and then kind of just negotiate terms with you, and then the execution of a license agreement. We try to make that as streamlined as possible to gain you access to the technology. And we value you as a partner so that you could also, engage with the lab to get further research done under either CRADAs or SPPs, which I think Mike will talk you through. And then we also have a lot of materials to help assist you through that process. We have a licensing guide, we have a partnering guide, and then our staff is always available to answer questions for you and help connect you with ORNL researchers. So thanks very much.
Great. Thank you, Eugene. In addition to licensing, and for those of you who have licensed from a university, we look a lot like a university when it comes to putting in place a license agreement. We have other mechanisms where our researchers can actually collaborate shoulder to shoulder with you or perform work on your behalf. And these are called strategic partnership projects. That used to be called work for others, and then cooperative research and development agreements. So really quickly, a strategic partnership project is a classic sponsored research project where an external partner funds an ORNL scientist to do work on their behalf at essentially the same cost that it costs DOE to do work. So we call it a full cost recovery. In a strategic partnership project, the statement of work only has tasks for the national laboratory. And if the sponsor is a U.S. company and is using non-federal funds, then the results of the research results can belong to the partner. So if our scientists invent something in the course of doing a strategic partnership project, and again, if you're a U.S. entity using non-federal funds, then you can take title to those inventions so long as you promise to patent them. And similarly, if there's data that results from the project, you can take title to that data and treat it as your proprietary information. Now, a cooperative research and development agreement anticipates both we and our partner will work together on a project. And it also anticipates that the work that we do will most likely be funded by the federal government. And so if you look at a statement of work for a CRADA, you'll find that the statement of work has tasks for both parties. The CRADA provides for exchange of personnel, so our scientists can come work on your site, you can come and work on our site. And because the expectation is that the partner will be paying for their part of the work and we'll be paying for our part of the work, rather than having the ability to take title to the research outputs, you have the ability to control them either through a license or through a protection. And what I mean by that is if our scientists invent something while working on a CRADA, the lab will take title to it, but the company that's partnering with us has an option for up to an exclusive license in a negotiated, pre-negotiated field of use. And if we produce data, you can ask that data be treated as what we call CRADA protected information. And that data is able to be held as if it were your proprietary information for up to 5 years. But after that 5 years, it does become publicly available. So the notion is that an SPP, you pay full cost, you have a little bit better IP position. On a CRADA, typically we each pay for our own part. You have the ability to control the IP, but it's not as robust a position as if it were an SPP. We also have a series of what we call user facilities. We have 8 at Oak Ridge National Laboratory, and these are facilities that are intended to be bigger than you would even be able to find at a university. It's supposed to be something close to a one-of-a-kind capability, and we make this capability available to prospective partners at no cost so long as they agree to publish the results. And so some examples, we today have the world's fastest computer. So if you have a computational problem that is appropriate for a computer that large, then you can be selected to do work on the computer. And again, that access is at no cost so long as you agree to publish your output. We have a manufacturing demonstration facility with similar capabilities. We have a nuclear reactor, and we have a neutron source with similar capabilities. So these are meant to be very large, essentially unique capabilities that the Department of Energy makes available to scientists in return for making their research results available. So that is partnering with the National Lab in a nutshell. I suspect you're much more interested in answers to technical questions, so I'll go ahead and go through some of the questions that we have. And we'll begin. The first question, and actually this question, Eugene, goes to you. Is licensing of this technology available to companies outside of the United States?
So Mike, thanks very much. Yes, it is. We're offering it non-exclusively to a lot of our clients. We have patents under prosecution in a number of countries. So I have a PCT following, but we have US, Canada, Mexico, and EP rights that we're seeking. Generally, our licensing agreements, though, would request that the company manufacture substantially within the United States. So that's something to keep in mind. But for this particular technology, it's a subset of an overall system. So you may be able to, fractionate out the development of the coils and the electronics in the United States and then put it in, a foreign vehicle or something like that.
Great, thank you. Next question is technical. For moving vehicles, is there a braking force created by the charging magnetic field? And Omer, I'll hand that off to you.
Yes, sometimes we get that question. So in our magnetic field approach, there are no magnetic forces that may be effective on the vehicle. Sometimes we are asked that question, how about that rotating magnetic fields trying to spin the vehicle around? There's no such effect. And similarly, in dynamic wireless charging applications, there is no braking effect of the magnetic field that we have that would slow down the vehicle.
Excellent, thank you. Next question, and appreciate the introductory remark. Impressive performance, I agree. Are you pulsing each coil different than single coil approach, i.e. different frequency, or is it the same pulsing and just 3 coils overlaid with rotating coil pulse control?
So 3 coils are not necessarily overlaid on top of each other. We actually have 2 layers, 3-phase approach. So coils are more or less 120-degree pizza slices. And then at the top layer, we have the 180-degree rotated version. And then that gives us actually 3 double D coil pairs that are 120 degrees spatially phase shifted, and we electrically excite them with 120-degree electrical phase shifts. So instead of power being pulsed, we have constant power transfers, and then that happens with the rotating magnetic fields. So that's the difference.
Thank you. Another question, either for Mustak or Omer. What is the gap between the 2 magnetic couplers and misalignment in the case that provided 96% efficiency with 100 kilowatt output?
You want to take this, Mustak?
Omer, I think you have more details.
Yeah, sure. So the gap between the 2 magnetic couplers for the Hyundai Kona, it's about 4 inches. That's about 120. That's actually 5 inches, 120 millimeter air gap. For Porsche Taycan, it's a luxury sports vehicle, so it wasn't possible to get very high ground clearance on that one. So that one has 120 millimeter distance between the surface of the vehicle side coupler to the floor. So that's actually the magnetic air gap definition of the SAE J2954. If you look at directly surface to surface power transfer distance, that's a little less than that, about 1 inch less than that, because our transmitter is also a little over 1 inch thick. So that gives us about 3 inches of power transfer distance.
And Omer, can you talk a little bit about the misalignment? Was it just perfectly aligned, or and then maybe kind of along with that, how does the efficiency roll off as you are misaligned?
Yeah, so we actually heavily tested our 100 kilowatt system for misalignment conditions. 4 inches of X direction, plus or minus, 4 inches of misalignment in Y direction, plus and minus. And then we also did combination misalignments, X and Y together. So we were still able to reach to the full 100 kilowatt power transfer level. And then the efficiency goes down by a fraction of a percent. So about 0.6 to 0.8% reduction in efficiency in those extreme misaligned conditions. Typically for 1 inch, 2 inch doesn't matter a lot, but 4 inches on the extreme corners, then the efficiency may go down by about 0.6, 0.8%. We also tested the system at yaw and pitch type of angular misalignment conditions as defined in the SAE J2954. And then we didn't see any sensitivity, so no efficiency drop, no power drop. We also did angular misalignments, that is the roll angle misalignments. J2954 specified plus minus 3 degrees of rotational misalignments, kind of getting into the parking line with an angle. That didn't change anything, so we wanted to do 15 degrees, 30 degrees, 45 degrees rotational misalignments, and that also didn't change anything in the system behavior. Same efficiency, same power transfers.
Excellent, thank you. You may have already answered this, but what is the clearance between the car and the floor systems?
Yeah, so Hyundai Kona, that's about 5 inches, and for Taycan, that's about 4 inches from the surface to the floor, but 3 inches from transmitter to receiver power transfer distance.
Perfect. And did you use the front truck of the Taycan for the ancillaries?
Yes, that's true. So on the trunk area, they had a compartment where they had the liquid cooling systems, the pumps and valves, and a lot of pipes and hoses. So above that, actually, we put our resonant tuning components and the rectifier that finally goes to the, that provides the DC output to the system. So in the newer Taycan, even though we may pack every component that we have today, that still gives a nice room for a carry-on or a bag that you can put. In the earlier version of Taycan that we have, we actually used more or less the whole space for the 270 kilowatts receiving side electronics.
Okay, perfect, thank you. This is your crystal ball, when do you think we'll be able to see these products become commercially available?
So it's been just 2.5 years that the standards actually came out on this technology. So it's relatively new system, the wireless power transfer in general. So as more companies invest in this, now we have standards in place. Of course, technology developments never stops, right? So our Polyphase actually couldn't make it to the first edition of the standards out there. However, in the new revision of the standards, Polyphase will likely be included as one of the reference designs because there's a lot of demand from automotive OEMs, and we have active partnerships with Volkswagen, Hyundai, Stellantis, BMW, and many more are coming. So a lot of OEMs are also making engagements with the tier ones to actually manufacture this technology. We already have a few companies received licensing applications. One of them already has the commercial license. So there's more coming in. So hopefully we will improve our research prototypes into manufacturable, commercial grade, more cost-effective systems in just a few years, and we will see our technologies in production vehicles. I think just a few years.
Excellent, thank you. Okay, now this relates to the in-motion wireless charging. Typically, how far below the road surface would the ground coupler be?
So for the dynamic charging system, already we're working with American Center for Mobility to actually integrate our transmitter coils into the roadways, and they had a requirement 3 inches below the pavement. However, we started working more closely with the Department of Transportation and see how they would actually integrate our systems into the roadways. And they are working with another university's asphalt laboratory to do some of these tests. And we plan to actually worked with them closely for the next phases of the project. So they said there's no such requirements that the transmitter needs to be 3 inches below the pavement. So that actually reduced the power transfer distance by about 3 inches, because we were planning to use about 6 inches vehicle ground clearance and another 3 inches for the transmitter being embedded below the pavement. But apparently that's not really a requirement. As long as the concrete encasement for the transmitter can handle the shear forces of the class 8 trucks rolling over it, then there's no additional layer of asphalt or concrete that needs to go over the transmitters. So yeah, that's what it is.
Thank you. Now, this one relates to charging in a residential application. Does this system require three-phase charging or three-phase power?
Yeah, that's a very good question. So three-phase is only required at the high frequency stage. So in residential home garage charging applications, you still take the single phase from the grid, and then you convert it to DC, and then you have the three-phase inverter. The high frequency inverter converts it back to three-phase. So the grid integration for the residential home garage applications can be still single phase, but we do the conversion for the polyphase coils with a three-phase inverter.
So is that true for all of your applications, that you do a conversion to DC before you do the polyphase?
Absolutely, that's right. So for power levels less than 11 kilowatts, you have the single phase on the grid. But for power levels 20 kilowatts and more, you also require three-phase connection on the grid side. So grid needs to be three-phase, coils are three-phase, but the power is relatively low, then single phase is okay for residential or small commercial deployments. Single phase from the grid is needed.
So this one relates to, say, having a number of facilities, say, for example, a UPS packing facility. How many vehicles could be charged simultaneously?
So it really depends. Some of the UPS facilities are really at the size of a small town. They even own and operate their airports. Their World Hub in Kentucky, the Sandy Creek facility in Atlanta, and a couple of others, I think in California. They have hundreds of vehicles. Currently, they have actually low power package delivery vehicles. For Class 8 vehicles, it's still an ongoing research. I think there are systems they can provide a few 100 kilowatts, 150 to 200 kilowatt systems. And one thing that UPS or other delivery companies practice is that they try to reduce their dependency from the grid. I know your question relates that if you have hundreds of vehicles charging simultaneously at the UPS facility, that may collapse the grid, or it may have negative impact on the grid. However, they are doing a lot of investments on on-site power generation using solar photovoltaic panels, on-site microturbines even, energy storage systems, bidirectional capabilities on the vehicles, so they can optimize the microgrid operations. They can also add more on-site energy generation assets to their facilities. That way, actually, not just providing the electric vehicles charging, without any grid impact, they also ensure that they have kind of an independency from the grids, because if there are power outages, packages will get delayed, packages will get lost. So that's a lot of financial burden on the company. So they are making a lot of investments on on-site power generation, microgrid optimizations, bidirectional charging systems, energy storage systems. So you can actually during the day store energy, and when the trucks get back to the facility, you can do overnight charging using the energy previously stored on the batteries.
Great. Now, this one may be related. Question is, the circuit diagram indicates that vehicle to X is not possible with the current design. Could you discuss if V2X is possible or being considered in the future with wireless charging?
Yeah, so we have actually bidirectional systems explored in other projects. On this one, actually, we don't want to do bidirectional because the application area is really the interstate extreme fast charging systems, because after driving 2-3 hours, we all take 10-15 minute breaks, right? So within the 10-15 minute breaks, can we put enough energy to the vehicle to be able to drive another 2-3 hours, right? 200 miles or so distances. So you don't want to provide power back to the grid. This is not the application this time. Here, actually, you want to pick up charge in 10 minutes and be able to drive another 2-3 hours. That's why actually the focus was not really the bidirectionality or V2X. However, the diode bridge rectifier on the vehicle side can be replaced with an inverter bridge, similar to what we have on the primary side. Of course, it'll be a little larger. With that, we can have bidirectional operation. So one thing that he can practice is that for high power systems, it can be unidirectional because you just want to charge the vehicle and get back on the road. But while it's plugged in at home, you have that full 12-hour, 14-hour window available for you. Then a relatively low power inverter could be there to do the bidirectional operation when needed.
Perfect, thank you. Now, this is more of a comment than a question. Have you thought about hardening the system against copper theft, which has been an issue that the electric utilities deal with?
So copper theft is an interesting question, but yeah, with wireless charging systems, actually, a lot of the public charging installations are thought to be completely underground, embedded into the roadways and pavements. So that actually provides a good level of protection against the copper theft. And I think in home garage residential installations, you don't have to necessarily do that. Transmitters can be sitting on the floor because it's the home, and it's kind of more secure than the streets, in public.
Here's a good question. How does the cost of a 100 kilowatt polyphase wireless charging system compare with that of a 100 kilowatt wire system?
And that's a really good question too. So even though, so sometimes I don't know if the person asking the question has the same thing, but a lot of times we see a misconception in the wired and wireless charging systems, right? For wired charging systems, plug-in charging systems, people think that it's so simple. It's just a pair of wires. Nothing can be more efficient than that. But it's not real, because even a plug-in charging system has 4 or 5 power conversion stages, because they need to take the power from the grid, they need to have a transformer, or they need to have a rectifier, inverter, high frequency isolation transformers, another rectifier, a lot of times a DC-DC converter. So that's already 4 or 5 power conversion stages. So 100 kilowatts wired charging system costs about the same as the 100 kilowatt wireless charging system. The only difference in the power architecture is the high frequency isolation stage. In the plug-in systems, they have a closely coupled transformer on a magnetic core. In our systems, it's actually planar, and it's a little larger, but it uses about the same active magnetic components and the same amount of copper wires.
Thank
So
you.
cost is very similar.
Similar question. What's the switching frequency selected here? And how do you manage high efficiency at partial or light load conditions?
So the switching frequency is defined in SAE J2954 is 85 kilohertz center operating frequency, but they define a range that can be anywhere from 79 to 91 kilohertz. So we typically operate around 84, 83 within that range. And how we manage to remain at high efficiency at partial or light load conditions, that's actually a feature of the magnetics that we have in the system, in addition to the silicon carbide wide bandgap devices that we have. So a lot of times the switching frequency needs to be around 20 kilohertz or so in plug-in charging systems. And with that, they use actually insulated gate bipolar transistors. They have actually a lot of conduction losses, a lot of switching losses. In light load conditions, their efficiency will be worse. In our case, actually, with the wide bandgap materials, silicon carbide, we kind of inherently get the higher efficiency even at the light load conditions. So that's a little bit magnetics, a little bit power electronics.
I think we have time for maybe two more. And I don't know if you can answer this one. What's the inductance and capacitance value for the polyphase coil? And is the inductance sensitive to environment? And if it is, does that give you challenges with controlling the system?
So the coil inductance is on transmitter, it's about 15 microtesla. On the receiver, it's about 9 microtesla. So the inductance is it doesn't have a good or strong sensitivity to the environment. It has a little bit of dependency to the current that it carries, and very slightly coupled to the temperature, but not a lot. So that inductance doesn't necessarily change, and that's usually within the tolerance of the system operation. That doesn't really cause any trouble in the control.
Perfect. And we'll have one last question. And to our attendees, thank you very much for this fabulous set of questions and this dialogue. It's been a lot of fun. Last question, what kind of cooling system do you use for the 300 kilowatt system?
We have liquid cooling systems. So both on the primary side and the vehicle side, we have liquid cooled systems, but similar automotive cooling coolants, ethylene glycol, 50-50 mixed with water. That's similar to what you use in your engine coolants.
Perfect. Well, Omer and Mustak, thank you so much for a wonderful presentation today. If you'd like more information, our contact information is in the chat. If you forget to take that down, just look up Oak Ridge National Laboratory and Partnerships Office, and I will make sure any questions you have for these scientists will be forwarded directly to them. Again, also thank you to OTT for providing this forum and for the opportunity to share the work that these folks are doing at Oak Ridge. Thank you all for joining us, and I hope you have a great rest of your afternoon.
Thank you very much.